We are delighted to bring you this educational activity presented by AACC and generously sponsored by Bio-Rad Laboratories. Today's webinar is titled Best Practices to Recover from an Out-of-Control Event, a Systematic Approach. Our speaker is Dr. Lauren Bachman. Dr. Bachman is Professor of Pathology and Co-Director of Clinical Chemistry at Virginia Commonwealth University Health System. She is currently serving the American Association for Clinical Chemistry Finance and Nominating Committee and the College of American Pathology Accuracy-Based Programs Committee. Dr. Bachman also serves as the chair of the Clinical and Laboratory Standards Institute Expert Panel on Clinical Chemistry and Toxicology. Dr. Bachman's research and clinical interests include development of laboratory practice guidelines, standardization of clinical laboratory assays, and quality assurance. Dr. Bachman, we are thrilled to have you today. And with that introduction, I will now turn it over to you to begin.
Okay, well, thank you very much to AACC for the introduction, and thank you to Bio-Rad for supporting today's webinar. So today's presentation will review a systematic approach to recovery from an out-of-control event in the clinical laboratory. So an out-of-control event occurs when a QC rule evaluation for one or more QC measurements produces unacceptable results. So these are my disclosures for this presentation. So after today's presentation, participants should be able to identify the first steps to take after an out-of-control event occurs in the laboratory, discuss how to evaluate the impact on patient results after an out-of-control event, and to determine when patient results need to be corrected, a process for doing so, and also how to implement actions that prevent recurrence of the out-of-control condition. The primary reference that will be used as the basis of the recommendations in this presentation is the Clinical and Laboratory Standards Institute document C24. Its title is Statistical Quality Control for Quantitative Measurement Procedures. This CLSI guideline issues recommendations for designing an effective QC strategy, selection of QC materials and frequency of QC analysis, establishment of QC target means and standard deviations, troubleshooting guidelines, and recommendations for how to recover from out-of-control events. The document can be found on the CLSI website, which I've listed the URL at the top of the slide. So laboratory errors have been shown to cause harm to patients and also increase the cost of healthcare. So in one study, the investigators examined more than 40,000 laboratory measurements conducted in a high volume stat lab over a time period of 3 months. They found an error rate of almost 0.5%, which is a significant error rate. The study showed that 6.4% of laboratory errors led to incorrect patient care decisions or inappropriate treatments. 19% of the errors resulted in an unnecessary diagnostic workup that increased costs to the patient and the healthcare system. This slide shows different categories of laboratory errors and their sources. So a study published in Laboratory Medicine in 2012 found that errors in the pre-analytical phase, like specimen mislabeling or specimens collected into the wrong container type, constituted the majority of laboratory errors. Errors in the post-analytical phase, including incorrect result interpretation or failure to call critical values, also formed a large percentage of the errors. However, analytical measurement system errors did still represent a significant portion of the overall error rate. Another study that examined more than 670,000 proficiency testing survey submissions from 665 laboratories found that PT failures due to analytical errors consisted most frequently of instrument errors, like the instrument needed maintenance, or maybe the instrument had a pipetting malfunction, followed by calibration errors. For example, the assay was miscalibrated or calibrators were prepared improperly, and then reagent errors, such as reduced stability of an onboard reagent. So the laboratory's routine quality control program should be designed to evaluate the analytical performance of the measuring systems and to detect potential errors in the analytical phase of testing. To monitor the analytical phase of testing, QC materials should be integrated into the patient testing workflow and analyzed along with patient specimens at a frequency established by the lab. So for example, a laboratory may run QC every shift or every 12 hours. QC acceptability criteria are typically based on rules that assess the standard deviation intervals for QC results. The SDIs are calculated from the observed results compared to the QC target mean and target standard deviations. QC target means and standard deviations are established during initial method validation and then refined as a result of ongoing performance monitoring. In this slide, patient samples are represented by the blue striped rectangles, and the QC material is indicated by the black rectangle. The graph below shows QC results obtained over time, with the green bars representing the limits of the acceptable range. If the measuring system is performing as expected, QC will be within the acceptable range, and we're confident in the quality of the patient results we're reporting. However, if QC values exceed the acceptance limits, representing an out-of-control event, this may indicate an out-of-control condition where the measurement procedure is not performing as expected. Out-of-control conditions are usually identified by a shift or drift of QC values away from the target mean or an increase in assay imprecision. A QC drift, shift, or increase in precision identified by an out-of-control alert means that something happened to the measuring system that could be causing us to report erroneous patient results. So this slide shows some common causes of out-of-control events or QC failures. One of the most frequent causes of QC failure is a problem with the QC material itself. So the material could be improperly reconstituted by the laboratory, it could be degraded, perhaps the technologist analyzed the wrong level of QC material, or an inappropriate QC target mean or SD is used by the laboratory. QC can fail due to a problem with the reagents. So perhaps the reagent is improperly formulated by the manufacturer or improperly prepared by the laboratory. Reagents can exhibit onboard degradation or degradation during their shelf life when stored at their storage condition. Reagents may be improperly stored, or the lab could be using an inappropriate QC target mean for a new reagent lot. QC failures can also be caused by problems with calibrators, so improper formulation or target value assignment by the manufacturer. The lab could improperly prepare the calibrators, or the lab could be using an improper calibration frequency. QC failures can also be caused by instrument problems, so things like degradation of the lamp if the lab is using a spectrophotometric method, a leak in instrument tubing or damaged pipetter seals, mixer failures, and pump failures. Or the lab could have an inadequate maintenance frequency. So inadequate maintenance, inadequate cleaning or decontamination, wearing of parts without replacement in a timely manner. So all of those scenarios can cause QC failures. Improper procedures are also a common cause of QC failures. So failure to follow SOP, inadequate SOPs, or inadequate training for those SOPs. So this table shows an example of level 1 QC results for a total calcium assay, with our current QC values shown in the top row and historical QC values shown below. The current QC value failed the acceptance criteria and was flagged low, which is shown in red. You can see that the assay looks like it's been trending in a downward direction over the previous couple of days from a starting point at positive 1.4 SDIs from the mean at the bottom of the slide to negative 3.6 SDIs from the mean for the current result. And this result did trigger an alert. So what are the first steps that should be taken with this type of out-of-control event? So this slide shows a systematic pathway for responding to out-of-control events. The first step that has to happen is actual detection of the analytical measurement system error. An automated QC rule needs to fire to alert the technologist of a potential problem, or the technologist needs to recognize that the result has failed acceptance criteria if the lab is using a manual QC review process. Once a QC alert is received, the first thing the technologist should do is immediately stop reporting patient results. The QC alert means that there is potentially an error in the analytical measurement system that could cause harm to patients. Therefore, results reporting must be stopped and the issue needs to be investigated. The next step is to perform an investigation to determine the root cause of the problem. The root cause is the actual reason for the presence of the analytical measurement system issue. So oftentimes a problem is initially identified, but it's actually not the root cause. For example, QC may fail due to calibration drift, and that issue is corrected by recalibration, but that's not the real problem. It's only signaling an underlying problem. Perhaps the routine calibration frequency is inadequate for the stability of the reagent, or maintenance is not being performed frequently enough and the instrument is becoming contaminated. So it's really important to determine the actual root cause so that that cause can be directly addressed through corrective and preventative actions. Then the fourth step is to implement corrective action to correct the problem so that testing can get back up and running as quickly as possible. It's not uncommon that we feel like the response to a QC failure ends with corrective action. Fantastic, we have fixed the problem and now we can resume patient testing. However, there is still a number of steps remaining to adequately recover from the out of control event. So the next step is to evaluate the impact of the out of control condition on previously reported patient results. So if we're running QC every 12 hours and we have an out of control event, the actual analytical measurement problem could have happened 6 or 7 hours ago, and we've been reporting erroneous results without realizing it. This means that previously analyzed patient samples need to be reanalyzed after corrective action has been performed to determine if the magnitude of the error was such that the error could have caused a clinical impact like wrong patient treatment based on those erroneous results. Then we need to mitigate or reduce any potential patient harm that resulted from the erroneous results. This is accomplished by issuing corrected reports and calling those corrections to the ordering provider so that they are aware of the issue and can take any necessary steps to change their clinical course of action. Broad communications may also need to be issued to all of the laboratory's clients. The last step of the recovery process is to implement a preventative action. So preventative action is not only correcting the problem in the short term, but ensuring that the problem does not reoccur. That could mean replacing parts or scheduling instrument maintenance more frequently, or changing onboard expiration dates so that reagents are changed out more frequently, or even changing the QC rules so they detect the problem earlier. Of course, be sure to document the entire response to the out of control event from the point of error detection to the final preventative action plan. And then be sure to evaluate the effectiveness of the preventative action plan as part of the laboratory's routine quality management program. So to quickly detect an analytical measurement system error, an effective QC program needs to be established. The QC target means and standard deviations should be determined using an adequate amount of data. So the CLSI C24 document recommends analyzing new lots of QC for at least 10 days to establish a target mean for the new lot of QC. Remember that the standard deviation is not a function of the new lot of QC material, but is rather a function of the analytical measurement system performance. Therefore, target SDs should be calculated using historical data, usually including several months of QC data, to incorporate multiple sources of normal variation like different calibration events and different routine maintenance activities. QC multi-rules should be established to detect increased random error or imprecision and increased systematic error or shifts in trends. So for example, a set of QC multi-rules might include a 1.3S rule, a 2.5S within and across control rule, an 1.5S rule where the alert triggers if there are 8 values that exceed 1.5 standard deviations from the mean in a single direction, or a range 4S rule. So this rule will fire when 2 consecutive QC results have 4 SDs or more between them. So laboratory technologists should also be examining Levy-Jennings charts whenever alerts fire to determine if an out of control condition is occurring. Once an alert is detected, the technologist should ensure that all patient result reporting is stopped for that assay. This could include taking the assay out of service or even taking the entire instrument offline if necessary. Be sure to check that auto verification is turned off if auto verification is performed in your lab, so that results are not automatically reported into the medical record. The second step is to quickly determine the scope of the problem. Check the other levels of QC for that assay to see if they're affected. Check QC for other analytes on the same instrument to see if they're also affected, which could suggest a global instrument problem and that the entire instrument needs to be taken offline. Also check QCs on other instruments to see if the problem is affecting multiple instruments. That would clue you in that the event is due to something in common with multiple instruments, like the reagents, and would suggest that you need to take the assay offline on more than one instrument. You definitely want to look for other QC values that are about to fail the QC rules, so you can gain more insights into the nature of the problem and can figure out which assays or instruments you need to immediately take out of service. Once the assay or instrument is taken out of service, troubleshooting can begin. We can examine the Levy-Jennings charts for the calcium level 1 QC to see if there are any shifts or trends that are developing, and if we can pinpoint the actual date and time the problem started. We can check the laboratory records to see if any new reagent lots or new calibrator lots were first implemented when the problem started. We can check the status of the maintenance for the instrument. So were there any recent maintenance issues or instrument parts replaced? So these types of investigations can provide clues about the root cause of the problem. The good news is that we do have tools to evaluate recent assay performance. Of course, we can examine the Levy-Jennings charts and take a look at our QC multi-rule performance. We can examine our daily, weekly, and monthly QC statistics. We can check routine laboratory records, so our calibration records, our lot change records, our maintenance logs, and temperature charts to see if there might be any deviations that explain our QC alert. We can check other laboratory quality assurance records like 6-month linearity checks and among instrument comparisons. If the lab is participating in peer group QC programs, we can check the peer group QC data. But we can also check patient-based real-time QC monitoring data if the lab is implementing that strategy. And we'll talk more about that at the end of the presentation. So now that we have detected the error and stopped reporting patient results, we can examine the Levy-Jennings charts for the calcium QC as shown at the bottom of the slide. So we reviewed our records and nothing really seems amiss, except for a slight downward trend in QC results over the past couple of days that could be seen on the Levy-Jennings chart. One of the first troubleshooting steps you can perform to determine the root cause of a problem is to repeat the QC analysis using a fresh container of QC material. Do not just repeat the QC from the same aliquot or vial of QC material, because this does not really constitute an intervention. Really, the only thing you'll learn by repeating the QC from the same vial is if perhaps the instrument had a misaspiration. So you actually want to go into the refrigerator, obtain a new unopened vial of QC material, and repeat the measurement on a fresh aliquot of the material. If the repeat passes and the repeat result is not in danger of failing an acceptance rule or about to fail again, then a problem with the material used for the initial QC run is likely. So some common problems with QC material include the QC material itself was evaporated or improperly stored. The QC material is nearing its expiration and has degraded. The wrong level of QC was analyzed. The QC material was damaged during shipping if a new lot or the lab has received a new shipment of the existing lot, or use of an incorrect target mean for a new lot of QC material. So the lab can investigate these issues by performing activities like checking the QC vial liquid level, checking the QC open vial expiration date, checking the expiration date of the unopened QC material, check to see if it's a new shipment, check to see if you're using the correct target mean for a new lot of QC materials. So you want to repeat the analysis using a fresh bottle of QC. If the repeat passes and is not near a limit of acceptance, then the root cause is likely an issue with the QC material itself. If the repeat passes, but only barely so, and is near a limit of acceptance, then the problem is not likely due to an issue with the QC material itself, and further investigation is needed. If the repeat fails, then the root cause has not been determined and troubleshooting should continue. In this case, degradation of the material in the QC vial that was being used for QC analysis was the root cause of the problem. It was likely left at room temperature too long or too many times during testing. When a fresh vial of QC material was analyzed, the value was acceptable, the repeat value was not near an acceptance limit, and there were no further issues. So the short-term corrective action was to use a fresh container of the QC material. So far, we have detected the out-of-control event, stopped reporting patient results, determined the root cause of the problem, and implemented corrective action. However, this is not the end of the recovery process. We still need to evaluate the impact on previously reported patient results, take steps to reduce or mitigate patient harm, and implement preventative action to prevent recurrence of the problem. The red bar shows the QC failure obtained in the previous example. The black bar represents the fact that acceptable QC results were obtained after corrective action was implemented. Now we need to evaluate the impact on patient results. Since the out-of-control event was due to a problem with the QC material itself, this would not have impacted patient sample results because there was actually no problem with the analytical measurement system. Therefore, previously reported patient samples do not need to be repeated. However, we do still need to implement preventative action. Since the QC material likely degraded, the laboratory modified the open vial expiration date so that fresh materials would be used more frequently. In the next case, an out-of-control event occurred for level 1 glucose QC. A look back at the Levy-Jennings charts showed a trend had been developing over the past several QC runs. So the first thing that the lab did was repeat the analysis using a fresh vial of QC. That did not correct the problem. Therefore, we know there is likely a problem with the analytical measurement system. The next step we took was replacing the reagent wedge, because we know that an unstable onboard reagent is a frequent cause of QC failure. We replaced the reagent wedge and repeated the QC, but the repeat was still not acceptable. We then recalibrated with a freshly prepared calibrator, repeated the QC again, but this still did not correct the problem. Finally, technical service was called and a small leak was found in one of the instrument pump seals. So we determined that the root cause of the out-of-control event was a leaking instrument pump seal. It is important to note that technologists should not just keep repeating QC until it passes. So in this case, after repeating with fresh QC, a repeat failed. Sometimes the technologist will just try another repeat. In this case, the repeat would have passed. However, if QC was repeated more times, the technologist would have realized that the whole distribution of results had shifted, and a few values actually passed due to the natural imprecision of the assay. But there is a real problem with the assay, and you can see that because the whole distribution of results has shifted. This is also a reason why you should continue to investigate if any repeat QC value just barely passes after an out-of-control event. The root cause of our glucose QC failure was a leaking pump seal. Because the analytical measurement system was not performing as expected, we don't know when the problem started, we need to repeat previously analyzed patient samples. One approach is to repeat all patient samples between the time the QC failure was detected and the time of the last acceptable QC, when we know the analytical measurement system was performing as expected. However, if your lab is a high volume lab, this could be thousands of samples that would need to be repeated. One strategy to reduce the number of repeats required is to test subsets of patient samples at different time points between the failure and the last acceptable QC result to narrow down the time frame of the error. For example, you could repeat patient samples in groups of 10 at different time points. If results are compared before and after correction of the issue, we can identify the time of the event for the out of control condition, because this is when the repeat values would not match the originally reported results. So this slide shows, in fact, that although most of the patient samples did need to be repeated, a fair number of them near the beginning, near when we actually had the good QC result, did not need to be repeated. So this slide shows a scenario where you may not need to even repeat all patient sample concentrations if only a single level of QC fails. Level 1 glucose QC was acceptable, but level 2 failed high in this example. The root cause was found to be an inadequate calibration frequency, and it was corrected by recalibration. In this case, since level 1 QC was not affected, it was only level 2 that failed high, you would only need to repeat patient samples that exceed the target mean for level 1, because you know that all the values at the level 1 target mean and lower are not affected. So you would not need to repeat values that are less than the target mean for level 1. However, you need to be very careful using this strategy, as it depends on which QC levels are affected, on the magnitude of the error, and also the direction of the error. So how do we know whether the error is significant enough to require corrected reports? If QC target means and SDs are set appropriately, QC should alert for events that are not yet clinically significant. That's the actual goal of an effective QC program, to catch errors before they adversely impact patient care. However, some events may indeed be clinically significant and corrected reports need to be issued. So to help evaluate the impact of an out of control event on patient care, the allowable total error should be established. The allowable total error is defined in the CLSI EP21 guideline as an analytical quality goal that sets an overall limit for acceptable imprecision and bias for the result of a single measurement. And is used to establish the maximum error limits that can be tolerated without adversely impacting medical decision-making. This graph shows the distribution obtained when performing measurements on a patient sample, with the actual concentration of the analyte in the patient sample represented by the mean. The lower and upper limits, shown by the orange brackets on the graph, indicate the allowable total error limits. If after correcting the problem, the original erroneous value was within the total allowable error limit, an example is shown by the green star, corrected reports do not need to be issued because a clinically significant impact of the error is unlikely. However, if the original erroneous values fall outside the allowable total error limit, as shown by the red star, then a clinically significant impact of the error is likely and corrected reports need to be issued. The European Federation for Clinical Chemistry and Laboratory Medicine held a conference in Milan in 2014 to establish recommendations for how to determine allowable total error. So they recommended that the preferred way to determine allowable total error goals is based on information obtained from clinical outcome studies, which can be found in the scientific literature. Professional practice guidelines are also a good place to find allowable total error recommendations. A second way that allowable total error can be established is using information obtained from biological variation studies. So biological variation is the normal variation of an analyte concentration when the patient is in a stable physiological state. Biological variation estimates can be found in databases, such as those published by the European Federation for Clinical Chemistry and Laboratory Medicine. Allowable total error can also be established using state-of-the-art assay performance. This information can be found in the scientific literature and among other sources. So this is an example of where to find biological variation data for the purpose of establishing allowable total error for an assay. You can visit the EFLM biological variation database. So I put the URL there at the top of the slide. Here, I've searched the database for serum glucose. The database provides estimates of biological variation from a meta-analysis of published studies. And you can see those at the bottom of the slide. The database has a tool called the Analytical Performance Specification tool here in orange. And so that tool can be selected. The tool then calculates the allowable total error based on the equation shown in orange, which contains the biological variation estimates. So for example, the minimum allowable total error for glucose based on biological variation is 9.6%. It should be noted that allowable total error may be different for the same analyte used in different clinical utilities or for different concentrations of the analyte. So for example, the allowable total error for glucose measured by glucose meters in hospital settings based on the clinical impact of insulin dosage errors is 12.5% for glucose values greater than or equal to 100 mg per deciliter. The laboratory director should make the final decision regarding the allowable total error selected for a particular analyte. So once we know the allowable total error, for example, 10% for glucose, we now have some criteria to decide if corrected reports need to be issued for patient samples after an out of control event. In this example, any patient sample where the difference between the repeat result after implementing corrective action and the original result exceeds 10%, that patient would be issued a corrected report. So in order to perform this evaluation quickly and accurately, the lab can build a tool to automate this evaluation process. So the technologist can enter the original patient results and the repeat results, and the tool will automatically calculate the percent difference between the original and repeat value and determine which results should have a corrected report issued based on the allowable error. Development of these kind of tools enables expedited review and more automated decision-making for the technologists. Corrected reports are then issued to accomplish the next stage of the recovery process, which is to mitigate or reduce patient harm. Some approaches to mitigate patient harm after an out of control event include development of these types of data entry templates to quickly identify patients that require corrected reports, establish procedures to call in extra staff to assist with patient sample repeats and provider phone calls, issuing memos to clinical staff in real time explaining the nature of the error and the impact on the patient results, and ultimately to engage risk management or institutional safety teams if necessary. The last step in our recovery process is to implement preventative action. The preventative action should seek to prevent the root cause of the problem. So for example, the root cause of our glucose problem was a leaking pump seal. Therefore, the lab would want to implement more frequent preventative maintenance activities that include pump seal replacements to prevent recurrence of this problem. One common type of preventative action is a more robust or frequent preventative maintenance program. The next couple of slides show some additional types of approaches for effective preventative actions. A common preventative action to prevent reporting of erroneous results is to increase the frequency of QC analysis. The regulatory minimum is 2 levels of QC analyzed per 24 hours of patient testing, but many laboratories choose to analyze QC more frequently, like once per shift or even once per every few hours. Increasing the frequency of QC analysis should be considered if the assay is unstable, like the one shown in the graph. This assay is experiencing a rapid calibration drift. Therefore, we would want to analyze QC more frequently to catch when this happens sooner and implement preventative action, like shortening the time between assay calibrations. It should be noted that manufacturers' recommended QC requirements and calibration frequencies are only minimum recommendations. The laboratory can always choose to run QC more frequently or calibrate more frequently to help keep the assay stable. QC should be analyzed more frequently if the lab performs large testing volumes in order to limit the number of patient samples affected from a single out of control event. QC should also be run more frequently if results are acted upon immediately with a clinical intervention. In this case, we would want to discover an error quickly so that physicians can be notified before an incorrect intervention occurs based on that erroneous result. Another way to prevent clinically significant errors is to ensure the QC alert rules are set appropriately to catch errors before they become clinically significant. One strategy is to base the rules on the sigma metric. The sigma metric relates the analytical performance or bias and imprecision to allowable total error as shown by this equation. For QC, the bias is typically set to 0 because we want to detect a change from the QC target mean. So that can be discounted. You can see from the sigma metric ratio that a high sigma metric, like a value of 5 or 6, indicates a low rate of error because the allowable error is large relative to the assay imprecision, while a low sigma metric, like a 3 or lower, indicates a very high error rate because allowable error is small relative to imprecision. For a high sigma method, a more generous SDI criteria can be used because small biases can be tolerated. You can see that the first graph shows a 6 sigma method. For this method, a small shift would not cause the values to exceed the allowable total error. Therefore, a larger SDI acceptance criteria could be used. However, if the method is a low sigma method, like the second graph, which shows a 3 sigma method, optimal analytical performance must be strictly maintained. For these types of assays, a more conservative SDI acceptance criteria are needed, and use of QC multi-rules to detect small shifts or drifts or small increases in precision should be implemented. This is because assay performance is poor, and even a small change in the distribution of results can cause a clinically significant impact. The laboratory can evaluate the analytical performance of the assay relative to allowable total error for all the assays they're performing in their lab, and then focus on developing stringent QC multi-rules if the assay has a low sigma metric. Another tool that can be used to prevent clinically significant errors is participation in peer group QC programs. These are offered by numerous manufacturers of measurement systems and also by manufacturers of QC products. For most peer group QC programs, users submit daily QC results to the program, and the program will provide a comparison of the lab's QC results to the peer group. So this one is for CBC analytes. The triangles are the lab's QC results. The middle line is the peer group mean, and the white boxes are the limits of acceptability. So in this program, a plus or minus 3 SDIs from the mean of the peer group is the acceptability limit. Historical data for that lot and previous lots are also provided. So an advantage of this approach is that data can be accessed in real time. If the lab experiences an out of control event, the technologist can access the peer group QC data to determine if the lab's QC value is significantly different than the peer group. And if it is, that would suggest a problem with the laboratory's measurement system. This peer group QC program is for oxyhemoglobin results from a blood gas analyzer. We can see the SDI for our lab was high compared to the peer group for 2 levels of QC. So we could tell that this issue was isolated or specific to our lab. This was resolved by replacing a new cartridge of the existing reagent lot on the analyzer. So the issue was caught before it could impact patient care. So through the use of peer group QC programs, results can be submitted in real time, allowing the lab to compare its results to the peer group. Using the data, the lab can also evaluate QC values for new lots of reagent or new lots of calibrator by comparing their values to those obtained by the peer group for that specific lot. The data can also be used by manufacturers to assist labs with troubleshooting. So in these ways, participation in peer group QC can lead to faster detection of analytical measurement system issues, identification of the root cause of issues, and faster recovery from the out of control event. Another tool for preventing errors is the use of patient-based real-time QC. In this approach, the laboratory's reported patient sample results are monitored in real time to detect potentially developing performance issues. If the analytical measurement system is performing as expected, and the analyte is stable in the patient population tested, then the average of patient results should stay the same over time. A trend in the results could indicate a quality issue. In this approach, a variety of ways to evaluate patient results on an ongoing basis can be used, such as moving patient means, moving patient medians, exponentially weighted means, cumulative summations, or other types of algorithms. The patient matrices are calculated after a defined number of patient results are reported, like after every 40 patient samples. The metric results are then compared against acceptability criteria based on allowable total error, SDI limits, or other modeling approaches. Alerts are then generated if the patient results begin to fail acceptability criteria, which can indicate a problem with the measuring system. This approach is very powerful and can be used to detect small changes in analytical performance that routine QC can miss. However, there are some variables that impact the effectiveness of the tool and that need to be optimized. So for example, the number of patient results to average needs to be optimized to implement this tool. The lab needs to come up with a way to identify outliers and extreme values and potentially exclude those from the analysis. The lab may need to investigate if different subgroups are needed for the analysis, maybe different patient populations. And this may not be useful for all analytes. It's especially not useful for analytes that tend to fluctuate widely in the patient population. Another thing that needs to be optimized is what magnitude of error should be used to trigger an alert. So here's an example of a patient-based real-time QC approach where the mean of every 40 patient results is plotted over time. The graph shows the limits of acceptability, and results that exceed those limits will create an alert. An out-of-range alert indicates a systematic error larger than the normal variation of the analyte in the patient population, and this condition could represent an analytical measurement issue. You can see here that the tool detected a systematic error. So the tool can detect an analytical problem earlier than routine statistical QC because it's being performed with a defined number of patient sample results, like every 30 or 40 patients. However, the technique can produce false alerts. So if an alert is received, the technologist should immediately review laboratory records to determine if there are any observable issues that need to be addressed and could be causing this alert. They should run assay QC immediately to actually confirm that there is a real issue. And they can always run previously analyzed patient samples to determine if there is a change in those patient sample results that would confirm the alert. Calculation of the sums of differences for QC values from a target mean is called cumulative summation. This is another powerful way to detect measuring system issues earlier than routine statistical QC. In this approach, the sum of the SDIs for a specified number of QC results is plotted. If the measuring system is stable, that sum should always be the same. However, if the sum shifts or drifts, as shown in this graph for sodium QC results, that means that an analytical measurement system problem may be developing. The advantage to this technique is a more sensitive or earlier detection of errors compared to the most widely used QC multi-rules, especially when routine assay standard deviations are large, like in a poor performing assay. The disadvantage is that simulations and modeling are needed to optimize the alert values, so technical expertise is required. However, automated tools for optimization and implementation are becoming available from the manufacturers. So in conclusion, a systematic approach should be implemented by each laboratory to respond to an out-of-control event. The approach should include two phases, where in phase 1, we detect the error, we immediately stop patient testing, we investigate and identify the actual root cause of the issue, and implement corrective actions so that we can get back up in testing. However, we should not forget to move to phase 2, where we need to evaluate the impact on previously reported patient results, take steps to mitigate or reduce patient harm, and implement preventative action to prevent the problem from reoccurring. Allowable total error should be used to evaluate the impact on patient results after an out-of-control event, and can also be used for designing an effective QC program that will prevent errors. Additional tools are available that can improve the ability to detect errors and prevent them from reaching clinical significance. So this concludes the presentation, and I will be happy to take any questions.
Right. Thank you, Dr. Bachman. We'll now take questions from the audience. As a reminder, please submit your questions via the Q&A box. So the first question that we have is, when repeating QC after an out-of-control flag, do you recommend repeating just the QC levels out or all levels of QC?
Okay, so that's an excellent question. Can everybody hear me okay?
Yep.
Okay, great. So if only one level of QC fails the acceptability criteria and other levels are not near the acceptance criteria or not about to fail, it's probably okay to begin your troubleshooting process by just repeating that one level that was out of control. However, if a out of control condition for the instrument or the measurement system is identified, then corrective action needs to be implemented. And after the corrective action, the laboratory would need to repeat all levels of QC to verify that the analytical measurement system is actually performing as expected.
Thank you, Dr. Bachman. The next question we've got, what should we do with some analytes which don't have biological variation values?
Right, so I think this question is referring to, how can we establish allowable total error limits if we don't have access to biological variation? So the EFLM database is very good, and there are a lot of studies in the literature that provide biological variation estimates. However, if it happens to be a new analyte or maybe an analyte that biological variation studies have not been performed, some additional approaches can be utilized. So one of them is to look at the literature for clinical outcome studies, and that's actually the preferred way according to the EFLM. So really look at the data coming from the clinical outcome studies first to determine the allowable error goals. If that's not available, then biological variation estimates can be used. Also, just state-of-the-art approaches. So you can look at scientific literature studies that look at the best analytical performance achievable by your measuring system to estimate the allowable total error.
All right, thank you. The next question we have is, I was wondering if you could comment on QC tips for qualitative lab essays, yes or no, positive or negative lab essays.
Yeah, so that is actually a really interesting question. So if an out of control event occurs for a qualitative assay and simply repeating with a new vial of QC material doesn't correct the problem, then there probably is an analytical measurement system problem that exists. So in this case, the lab would need to follow the systematic response to the out of control condition. So that's in the case where the assay provides just a qualitative result, a positive or a negative. However, a lot of assays that report a qualitative result also have a numerical result. And if that numerical result is sort of generated in the background, and then the instrument software will interpret that numerical result as a positive or a negative. So if you do have access to the numerical results, you can apply QC multi-rules to those numerical results and actually get a hint of when your assay may be drifting from its optimal performance by observation of a shift or a drift or increased assay imprecision in those numerical results.
Okay, thank you. Next question. Can you speak to how you prefer to set your SD ranges appropriately? More specifically, do you compare your SD to a peer group, or do you rely more heavily on total allowable error?
Yeah, so we actually set our standard deviation upon initial method validation. So using, like, if you've never implemented the assay before in your laboratory, then you have some data from your initial method validation studies, but that's a limited data set, and probably not all the sources of normal variation are included in that. So at that point, you would want to rely on your total allowable error, your clinical outcome studies. What is a clinically significant change for the analyte that we would need to be able to catch using our QC program? So really kind of the initial method validation data in combination with the other allowable total error approaches, it works out really well.
Okay, thank you. Next question. How many patient samples are needed to be repeated after corrective action is done? And what do you do for analytes that are not stable for repeat testing, such as CO2?
Yeah, so for the first part, how many patient samples need to be repeated after corrective action? That really depends on how many patient samples have been analyzed since the last proof that you have that the analytical measurement system was performing as expected. So if your lab is running QC every 12 hours, then you may need to repeat all the patient samples that have been reported since the last good QC result, which could have been 12 hours ago. Now, I did review an approach where you could analyze subsets of patient samples throughout that time period to try to narrow down when the problem occurred. So maybe it only occurred an hour ago, or maybe it occurred 10 hours ago. So by repeating subsets of patient samples and comparing the results after correction to the original patient results, you can try and narrow down that time frame. In the case of an unstable analyte, so let's say your analyte is not stable enough, you can't actually go back and repeat those patient samples. Well, then we would definitely, we don't really have an idea of the impact on the patient samples. You can maybe get some idea from, how big the impact was on your actual QC values, but QC, the utility of using QC is kind of limited because maybe you only have 2 concentrations, and of course your real patient samples are going to span the analytical measurement range or beyond. Probably the best approach would be to invalidate those results. You could also, I suppose you could try analyzing, maybe some PT materials or something, but again, those don't reflect real patient samples. So I think really the best approach would be just to invalidate those results, unfortunately.
Okay, thank you for that answer. What about bracketing testing with QC before and after the run, before reporting results?
Yeah, that is actually an approach used by some laboratories to ensure that their patient results are reported accurately. So this is where you would run QC at the beginning of the run all the patient samples, and run QC at the end of the run, and then you would report, you would wait to report the patient samples until your end of run QC passes. Then you can be sure that all those patient samples in between the first QC and the last QC, those were, those results are provided when the analytical measurement system is performing as expected. The problem is turnaround time. So if you bracket, your patient samples with QC and wait to do the reporting, then you're going to have, and probably an issue with turnaround time. Results are going to take a long time to be reported.
Okay, thank you. Do you have any comments on using split sample testing on different analyzers as a QC method?
Yeah, I think it's a good approach. It's all more quality assurance is always a good approach. So if you run real patient samples and aliquots, if you have access to that much material, then yes, that's a good approach. Run patient samples on one analyzer and the same aliquots of the same patient samples on another analyzer. Compare the differences to an acceptability criteria, and that would be a good approach. A lot of labs maybe don't have access to that much sample volume, and another limitation is you probably don't have enough material to use over a long time period, and we generally want our QC materials to last several months to a year, just so that we can have confidence in our QC target means
and so that we have historical reference values to compare to.
Okay, I think we have time for one last question. If one level of my QC doesn't pass, but the other two levels pass, can I start running patient samples while repeating the level that didn't pass in the background?
I would be hesitant to do that just because you haven't really conducted an investigation by that point. And so, it's probably preferable to just go ahead and determine the root cause of the problem. Make sure you understand the magnitude of the change and which concentrations of patient samples were affected. And of course, if you have identified an issue with the measurement system, then you're going to have to you're going to have to perform a corrective action. And that corrective action usually involves something like putting on a new reagent wedge or recalibrating. And if you perform a corrective action like that, you're definitely going to have to, perform all levels of QC to ensure that after the change or after the corrective action was implemented, the analytical measurement system is still performing now performing as expected.
Thank you for responding to all of those questions. That concludes this AACC educational webinar made possible by Bio-Rad Laboratories. We'd like to thank Dr. Bachman again for a great presentation, and we hope you enjoyed the program.